Okay, we are back. This is Calc 1. This is Chapter 4.9, Part 2. We had a bit of technical difficulty, so we're picking up on page 7. This is actually for Chapter 5, but 4.9 really fits in Chapter 5 more than it fits in Chapter 4. So we're looking at antiderivatives, and we're going to finish off page 7. We already did 1 and 2 on Part 1. And so here comes number 3. We are integrating. So remember, integrating, that's like finding the antiderivative. X squared plus 1 over x squared dx. And so what we're going to do is we're going to split this up. We're going to take this and write it as 2 separate fractions. And now we're going to do the each integration like one at a time. So we have the integration of 1 dx plus the integration of x to the negative 2 dx. And so when you're thinking not the derivative, the antiderivative. So what would I take the derivative of to get 1 for an answer? That would be x. And then this, I would add 1 to the power, and then divide it by whatever is left for the power here. So negative 2 plus 1 is negative 1, so I'm going to divide by negative 1, and then plus, there's always a constant, plus c. All right, and then that's about it, just a little cleanup. X plus, I guess minus, we'll go minus. Minus 1 over x, right, because that's x to the negative 1 power, so that just brings it down. The negative 1 power just takes it down. So there's example 3. Example 4 I can squeeze over here. So that is just t squared minus sine t of dt. So again, remember, you're doing the antiderivative. We'll just do each term. I'm not going to rewrite it out. You don't have to rewrite it out. You can just do it term by term. And so add 1 to that, that's 3. Divide by whatever the power is, that's 3. Now you got to think, right, sine, cosine, negative cosine. When I'm deriving, I'm going this way. When I'm integrating, I'm going that way. So if I go from negative sine up, it's going to be cosine. So just regular cosine plus cosine t plus c. And that's it. So, some of these are pretty quick, which is good. All right. It will get a little trickier as we go through chapter 5 here. So, number 5, we've got secant y tangent y minus secant y dy. Now, sometimes it's worth it to take these and make that 1 over cosine, make that sine over cosine, and make that 1 over cosine. This is not one of those times. I've done that already, and sometimes with integration, you try something and then you end up just crossing it off and either starting over or erasing it or what have you. This case, I'm going to rewrite it. I'm going to distribute, but you should recognize these as, right, secant tangent and secant squared, both of those. If I take the derivative of secant, I get secant tangent. If I take the derivative of tangent, I get secant squared, but there's a negative on it, so we can just have a negative 1 kind of along for the ride. And the derivative of tangent is secant, but then there's a negative 1 there, so there's the negative, and then plus c. And then we'll just clean it up. Secant y minus tangent y plus c. Number 6. Yeah, this one's a little trickier. You got to do a quick rewrite. So you've got the square root on the bottom. So I'm going to rewrite it, and then I'm going to rewrite it again. I'm going to simplify it. So we got x squared over x to the 1/2 plus 3x to the 3/2 over x to the 1/2 plus 1 over x to the 1/2. And that's dx. It's all dx. And now I wrote it separately because it was all over the square root of x, but I made all the square root of x's, x to the 1/2, and then I just kind of split up the band. So instead of having them all, think about when you add fractions. If I say 1/5 plus 2/5, I could say 1 plus 2 over 5, which is 3/5. If I take this step and go back that's what I just did there. That's how I split up those terms. That's mathematically, you are cleared for takeoff on that. So 2 minus 1/2 is 1.5, or 3/2. 3/2 minus 1/2 is 1. And that I'm going to write as a negative 1/2. Now we are going to differentiate. So now when you differentiate, here's the trick. You could just go x, and I'm going to add 2/2 to that, but I could just take the denominator and add it to the numerator. That's 5/2. That's the power, and then whatever the power is, I multiply by the reciprocal, because it's over 5/2. And so I'm divided by 5/2, which means multiply by 2/5. So I could just jump right to the multiply by 2/5. Plus, remember I add 1 to that. So that's 3x squared, but then over 2. Plus, I add 1 to that. So that's 1/2. And again, instead of writing over 1/2, I could just say times 2. Squeeze a 2 in front of that. And then don't forget the plus c. And you can just leave it like that. That's good. If you want to clean that up and write it more like 3/2 x squared, that's fine. Or you want to make that into a square root, that's fine. But this is good. All right. Let's see. Now they have a dy dx. So Leibniz. That's how Leibniz writes things. It's good for physics. You'll do that a lot with physics problems, the dy dx. So we got dy dx is equal to 2x plus 2. I just did the distributive property. It's 2 times quantity x plus 2. And they want solve the differential with 0.3 comma 2 on the solution curve. All right, so that means we're going to take the antiderivative of this, and then after we do that, we're going to substitute in 3 and 2 to find, we're going to find a general solution, but then we want the particular solution that contains 0.3 comma 2. So that's what's going on with this. So let's multiply both sides by dx. We can do that. So we got dy is equal to 2x plus 2 dx. And now let's integrate. So we're going to integrate this. We're going to integrate this. And so that's really 1 dy, kind of 1 dy. And so this variable determines what I end up with. So when I do the antiderivative of 1, it's just going to be y. Because when I take the derivative of y, that's just 1. But now how do I know it's a y and not an x? Because it's a dy there. All right, so that's where the y came from. And then what do? We add 1 to that, so that's 2. And there's already a 2 in front of it, but then we're going to divide. And then we add an x onto that, and then we say plus c. There's some constant. And so this is what we have now. We have this equation, y equals x squared plus 2x plus c. That is a general solution. But we want a particular solution that contains 3 comma 2. So we're going to put that in for y and 3 in for x. We're going to solve for z. Be careful on this. I know this seems silly, but when I was doing it in my head, I was just trying to rush through my notes. You got to subtract that off. That's negative 13. For a quarter of a second, I put 2/15 down and then quick scribble it out. And so, careful. It's super easy to make these mistakes when you're trying to get everything done just in your noggin. So we got x squared plus 2x minus 13. That is a particular solution. This is the general solution because it's got the plus c there. So that would be an example of way back on the first page when we were doing all the graphs. And it was like I could put a parabola with a, I could do this parabola plus 1, or this parabola plus 2, or this parabola plus 5, or this parabola plus 8. And it would just be this whole line of parabolas just slid up or down. Alrighty dighty. Excellent. Let's do page 8. So page 8 in your note packet for 5. I know this is 4.9, but it's in the 5 packet. So it says solve the differential given that the second derivative of x is x squared, the first derivative of first derivative of 0 is 6, and the actual function f of 0 is 3. And they want a particular solution. They don't want a general solution. So no problem. If we are after the first derivative and we have been given the second derivative, what we can do is integrate the second derivative. And so if I want the first derivative, I'm just going to do that. And so now I have f prime of x is equal to x to the third, because I add 1, and then I divide by 3, plus c. Now, note, I have this for the first derivative, so I know f prime of 0, so if I put a 0 in for x, c, I get out a 6, and so 6 is just equal to c. So now I have a particular solution for the first derivative. We got x to the third over 3 plus 6. All right, but that's not what they were after. They wanted the actual function. It says solve the differential given, and so they want us to find f of x. So we got to go this same thing. It's just f of x is going to equal the integral of f prime x dx. So that leads us to say, all right, f of x is then equal to x cubed 1/3 x cubed plus 6 dx. And so f of x is equal to, you add 1 to that, that's 4. 3's already on the bottom, but then times 4. Be careful. I've had students do this and they look at their own work after they've written it out and they end up saying 3.4. It's not, it's 3 times 4, that's going to be 12. Plus 6x plus c. And so now we know f of x is equal to x to the 4th over 12 plus 6x plus c. But we know that this is 3 when this is 0. 0 is nice because look, 0 to the 4th is 0, divided by 12 is 0, plus 6 times 0 is 0. So c is equal to 3. So our final answer, our final particular solution is f of x is equal to x to the 4th over 12 plus 6x plus 3. All right. So this was a general solution. This is the particular solution. This is what they were after. I guess I didn't have to box that one off. All right, let's look at a nice little physics problem from the moon. Here we go. We have vertical motion, so S, V, A. So if I take the derivative of S, I get velocity. If I take the derivative of velocity, I get acceleration. Integrating, I go back up the chain. So if I take the integral of acceleration, I'll get velocity. If I take the integral of velocity, I'll get my function S. All right, and so let's see. On the moon, the acceleration due to gravity is negative 1.6 meters per second. A stone is dropped from a cliff on the moon and hits the surface after 20 seconds. How far did it fall? What was the velocity at impact? Okay, so we do know enough. Most students read that and they're like, oh, nope, they didn't give us enough stuff. They did. We know velocity at 0 seconds is 0. We didn't drop it yet. We're just holding it there. We're going to drop it off the cliff and then measure it to see how long it goes. We also know that S of 20 is 0. Because when I put in a 20, it's going to hit the ground. It should be 0. The height should be 0. So this is the height at any given point. So, and we also know that acceleration is negative 1.6. And so here we are. If we take, if we want the velocity, we got to get the velocity first, and then we'll get back to S. So just like the problem we just did. We're going to take the derivative of acceleration of t dt. So what is that going to look like? Well, then we're going to say our velocity is equal to the integral of negative 1.6 dt. So velocity is negative 1.6 t plus c. So that was pretty easy to do the antiderivative there. Integrate it. Now we know this. So I can put a 0 here and a 0 there. And that means c is equal to 0. So my velocity formula is negative 1.6 t. All right. Now, we are going to use that eventually, but not right now, because they want to know the velocity when it hits. So we're going to put a 20 in there eventually. But just put a pin in that. We're going to do this again to find s of t. That's going to equal the integral of the velocity of t dt. And so that means s of t is equal to the integral of negative 1.6 t dt. So s of t is equal to negative 1.6 t squared divided by 2 plus c. So I can do that division, right? If you had got $1.60, you got 80 cents if you cut it in half. So negative 0.8 t squared plus c is equal to s of t. And now we also know it took 20 seconds to hit the ground. So we want this constant. The constant is going to be how high up the cliff was when we dropped it. So we put in 0, and we put in 20. So negative 0.8 times 20 squared. So you got to do 80% of 400. What is that, 320? Negative 320. So we got this. We got 0. Here, sorry, I kind of ran out of room. We got 0 equals negative 320 plus c, so we know c is 320 degrees. Or feet, meters. Sorry, not feet, meters. It's 320 meters. Ooh, that was a heck of a clip. All right, and now, we have this function, but we're not going to really need this. I still just want to write it out. There we go. So that's our function for the rock at any point in time. So I could put in after 1 second, how far did it fall? After 3 seconds, how far did it fall? After 10 seconds, how far did it fall? And we could calculate each thing, and we could graph it out, and we could do all that fun stuff. They didn't want that. They just wanted to know how far did it fall. So what was the height of the fall? That was 320 meters. And then they wanted to know how fast, what was its velocity when it hit? So we're going to use our velocity formula. So v of 20 seconds is negative 1.6 times 20. That means when it hit, it was going negative 32 meters per second. That would be the velocity. And again, in this course, like, you don't have to get the units right on my tests. You can put it on there and I'll fix it and I won't take off points. But in other courses, that's very important. In physics, they might be more worried about the units, or as worried about the units as the answer. All right, so that is 4.9 part 2. We'll see you for 5.1 next.